So we're going to start chapter 28 now, and it's called Fundamentals of Circuits. So we will start with connecting resistors to batteries for current flows. We will start with the simplest possible circuit, one resistor, one battery. And then we will have combinations of resistors in a certain combination called series and parallel. And then we will evolve from that. We will do, they don't have to be in series and parallel. So we'll show you two rules that you can solve any circuit in principle. And then you can add, to your resistors, you can add capacitors also. And and then it will affect the current. And they're called direct DC circuits because the current does not change direction. If the current, let's say, flows clockwise in the circuit, it will continue flowing clockwise. If you only have resistors involved, the current will keep the same direction and same magnitude. It doesn't change. If there is a capacitor, it will keep the same direction, but there is a chance it might change magnitude. A lot of times when the capacitor is fully charged, it will oppose the current. Eventually the current dies off. It will go to zero. So, yeah. I think everybody got this? And we're going to take advantage of this thing. V equal to IR, Ohm's law. So in the worksheet that you have, worksheet 8, we have lots of circuits in there. And it shows you circuit components. But I will just write them for reference. So we're here now. Okay. So circuit components, you don't want to keep drawing them like a cylinder to represent the resistor. So let's start with the ones we know. So batteries, usually it looks like this, right? This is the positive end, this is the minus end of the battery, and the voltage of the battery is called the EMF of the battery. So this stands just for the voltage of the battery. All right, so capacitors, we have seen them. Capacitor looks like this, right? C. The next thing we saw a switch. So switches, switch looks something like this. There is a gap, and this is the switch. In principle, the switch can close, it can open. If it's open, the current cannot flow. If it's closed, then the current could flow. Okay? If it's open, basically the resistance is infinite. V equal to IR, so the current will be V over R, but if R is infinite, I is zero. Okay. This is just a wire, right? Wire. The wires would be ideal. They would be ideal. By ideal would mean resistance is zero. If resistance is zero, V is equal to IR, the current will be some finite number. So R is zero. So what is I times zero? Zero. So the potential difference across the wire is always zero for an ideal wire. So that's good. Resistor will look like this. Something. And usually you draw enough of these to until you're satisfied and you say, okay, this is the resistor. So R for resistance. This is the resistance. Okay? We usually don't care about what material it's made of or whatever. You're just given one value. They say this resistor is 500 ohms. And we go from there. start with the simplest circuit, and then we go from there. So here's the basic circuit. You have a switch, and then you have a resistor here. This battery has the EMF, and this resistor has resistance R. Okay. How much current is flowing in the circuit? Zero, okay, because it's open. Yeah, no current flows yet. Now I would close the switch. Now the question is, in what direction will the current flow? Clockwise, right? It'll be clockwise. Why? Because this is the plus, and the direction of current, by the way, is where the plus charge will flow. So obviously, minuses that would be flowing this way, pluses would be flowing this way. So the current would be flowing this, would flow through the resistor, and then it would come out. So I will mention the Kirchhoff's loop rule. Instead of calling them rule 1 and rule 2, I'll try to just call them the loop rule and the junction rule. So it says if you add up all the changes in voltage in a closed loop, you get 0. So delta V sum over a loop equal to 0. This is true because the field is conservative, right? The electrostatic field is conservative. E dot dl over a closed loop is always 0. Now, let's analyze it for this case. So this is the rule, first rule. So let's do it for this particular circuit. And we choose a point where you want to start. You can choose your point anywhere you like. I usually like to start at the negative end of the battery and then go clockwise. But there is nothing wrong with starting at the positive end and going counterclockwise. Or starting here and going counterclockwise or clockwise. It doesn't matter. Any closed loop, the change would be 0. But I start here for the following reason, because I think it makes it simpler. When I go from here to here, I went from minus to plus, so the potential difference, the change in voltage is just the voltage of the battery, the EMF of the battery, so you get this. So what I'm going to write is specific for this circuit, not for every circuit. This is for all DC circuits. Here is what I'm going to write. So you get EMF. We're going to follow the current. These are wires. Is there a potential difference change? Is there a potential change on the wire? No, there isn't. So the wires is no potential change, so nothing. For the resistor, when I go from here to here, when the current flows from here to here, it flows from higher potential to lower potential. Remember? Okay. So the change would be positive or negative?
Negative.
Yeah, it would be negative because this is the higher, this is the lower, so the change is the final minus the initial, so it would be negative. So it would be minus the voltage drop across the resistor. This is a wire, so no change, and I'm back to where I started. And this says, I set it equal to 0. That's the total change. So that means, in this case, if I just have a resistor connected to a battery, then the EMF of the battery, or the voltage of the battery, will equal to the voltage across the resistor. Voltage across the resistor. But what is the voltage across a resistor related to
IR.
Yeah, it's I times R. I times by which law?
Ohm's law.
Ohm's law. That's it. So that is that. Let's do a slightly more complicated circuit. Here is that circuit. It will use this same rule. And let's see if we can do it. I'll do series and parallel, but so let's say I have a battery here. It's 9 volts. Then I have a resistor here. It's 4 ohms. And then I have another battery here. It's 6 volts. That's 6 volts. And then I have another resistor here. And it is 2 ohms. Now these two batteries, are they connected in a good way or in an efficient way or a bad way? It's a bad way. This is trying to push positives this way, and this one is trying to push them against it. So they're not helping one another. So it's like you have 2 water pumps. One of them pumping water this way, and the other one trying to pump it against it. So anyways, so effectively here, we really have a 3-volt battery. That's effectively what the voltage is. So if we're using a 3-volt battery, it's because they're going against each other. Intuitively, that's what's happening, okay? So the question, I think, what was it? Find the current and the potential difference across each resistor. So let's try to find the current and then the potential difference across each resistor. So let's call this one here resistor 1, and this is resistor 2, and let's call this one here EMF 1, and this one here is EMF 2, okay? So let's start with the loop rule. Now, do I know in what direction is the current flowing, or I don't know?
I
You know?
don't, but I can choose.
Intuitively, I will know, but technically, I can let the math do the job for me. Intuitively, here is my thinking. This is a stronger battery than this one. So this one would win, so the current will flow, this would go counterclockwise. This one is 9 volts, this is the bigger pump. So this is the positive end. So I think the current will flow counterclockwise. And I will show you, I will do it 2 ways. I will go with my intuition, say we'll go counterclockwise, and then the next one I will do it clockwise and just show you how it goes, all right? So I'm going to assume that the current is going counterclockwise, and I'm going to go around the loop starting here, right? So I'm going to start here and go around the loop. Okay. When I go from here to here, what's the potential change? What's the change in potential?
9 volts.
E1.
Yeah, E1 or positive 9 volts, right?
Yeah.
So let's call it, let's write the number, okay, 9 volts, positive 9. The current is going this way, I'm assuming it goes like this. So it goes from high to low.
Minus 4.
So minus
4i.
the voltage across R1, right? Minus V1.
4i.
So, and I will substitute the numbers in a moment. So minus V1, I will write minus V1 first. So minus the voltage across the resistor 1. Next, I'm here. When I go from here to here, I went from the positive end of this battery to the negative end.
Minus 6.
Minus
Minus
two.
6.
Yeah, so the negative has lower potential than this one, and it's lower by 6 volts. So minus 6. So minus EMF 2, which is 6. That's why I said effectively they're like a 3-volt battery. Next, we're here. Current still flows in this direction, right? You go from here to here. And by the way, since the current has no other path to take, it's the same current that flows through this resistor. It's the same number of charges that flow everywhere. Okay? So
Minus V2.
minus V2, right? Because it goes from high to low, so the low minus the high would be minus. So minus V2. And I wrote my equal sign, but let me try to. Nothing happens here with wires, and I came back to the same point. I looped. I went through the loop once, so I get 0. Now I'm going to substitute what V1 is and V2. So first, 9 minus 6 is 3. And that's equal to, move these to the other side, you get V1 plus V2. But V1 is I1, or the current, I times R1, right? Is the current times R1, so I times R1. And then V2 is I times R2. And it's the same current, I don't have to say I1 and I2. It's the same. Now R1 is 4, R2 is 2, so you get 4I plus 2I. What is that? 6I, right? You get 6I. So I get 3 equal to 6I. So that means I will be 0.5, right? 0.5 amperes? So, good. And I promised I would do it the other way. I would say, okay, let's say I have no intuition. I have to have at least some intuition. It has to flow clockwise or counterclockwise, nothing else, right? It has to flow within this circuit, so it's either going this way or this way. So let's say I get it wrong, I guess, I think it's going to go clockwise, clockwise. Let's say it's gonna go clockwise, all right? So let's do it now. And where do you want to start? I'm going to assume the current is going clockwise, and let's see where we go. So
Or
that's
6 volts?
R2.
here,
Yeah, the right.
here,
Yeah,
here.
to the right.
Here.
Yeah.
Okay, and now we're assuming our current is going this way, right? It will not be right, but I'm going to assume it to go this way, right? We said clockwise?
Yeah.
And I think Brian said I start here? That's good. So I go from here to here. The potential difference, it goes from high to low, that's my assumption. So it will drop by,
Minus V2.
So it would be minus V2, right?
Yeah.
Okay. And then from here to here, it will, what's the
6.
potential change?
Plus 6.
Plus 6, yeah, so plus 6.
Minus
And
V1.
then from here to here,
Minus V1.
minus V1.
1.
Yeah. So minus V1. And then here, from here to here,
Minus 9.
minus what?
9.
So minus 9, because we went from the higher to the lower, and we're back, right? To where we started, and so that tells me to put a 0 here. So 6 minus 9 is
Negative 3.
-3. Move it to the other side, so I get 3. Here I have negative V2 minus V1, so that's negative R2 times the current, right? R2 times the current. And what is R2?
2.
4, so minus 4I. And this one is minus 2I, right? Minus 2I. So I get minus 6I is equal to 3. And so I is equal to negative 0.5. So this tells me the minus sign, my current is actually the other way, because I got the negative. So it's saying, oh yeah, your assumption is not correct, that it's clockwise, it's, by the way, it's counterclockwise. And that's fine, yeah.
Wait, why is that wrong?
Huh?
Why is this wrong?
It's not wrong, it's telling me that the current is negative, so, meaning, I assume the current this way is this way, I assume that's the direction. The minus sign is telling me it's actually the opposite direction to where I thought. So you get, so the current is actually going counterclockwise, just like what we predicted at first. Now, what's the potential difference across R1, knowing the current now? So what is V1? What is V1?
4 times 0.5.
8? Oh, wait, no.
It's,
2.
It's IR, right? V1 is IR, so 6 times.
0.5 times 4.
0.5 times 4, yeah, 0.5 times 4, which is what? 2, and then V2 is
1.
0.5 times 2, which is 1, yeah. So what's the total? 3. And that's equal to, basically, effectively, these two batteries, put in this way, they're providing me with just 3 volts. Not the, if I oriented them the right way, I would get 15 volts, right? I get 15 volts instead of 3. They would add, yeah.
So even though they're like batteries in between the resistors, are they still technically considered as in series?
These two resistors?
Yeah, cause like,
Yeah.
I was just like messing around and I was like, oh, there's an R1 plus R2.
Yes, yeah, so, definition of series, if they have the same current, then they are in series.
Okay,
Yeah.
so if But if there was a capacitor in between them, something has
It
to
will still be in
happen.
series.
So they'd still.
There's no
Yeah.
junction.
Oh,
Oh, the junction.
Unless there is a junction, yeah.
Yeah.
If there is a junction, then it will be slightly different. Which brings me to, well, capacitors and, resistors in series.
Professor?
Yeah,
Good question. How do you know it's the same current? Because this 6 volt would give you a different current than a 9 volt, right?
Yeah.
So how do we know it's the
Oh.
same one?
well, this one is pumping some charges this way.
Yeah.
Let's say it's producing a certain current, and this one is producing its own current,
Oh, so,
but
okay.
the total, the net current is 0.5.
Got it, okay,
Yeah.
that makes sense. Thank you.
Yeah. you're welcome. If they had, what if this one, let's say this one is 9 volts, and let's say this one is 9 volts also, how much current would you get in that case?
0?
You will actually get 0, yeah, because 9 and 9, they will, they have the same strength, and they will end up being 0. You will see it from here, you get a 9 minus a 9, or here, 9 minus 9, you get 0. And it probably happened to you, it happened to me. If you put your batteries in like remote control or something and you put them the wrong way, then you get nothing. Especially if you put them the wrong direction, sometimes they will just cancel each other. But if you have 2 batteries, and
Yeah.
yeah, okay. Series, resistors in series. Resistors in series, they look like this. You got a battery here, and then you have resistor 1 and resistor 2 and resistor 3. It's usually enough to demonstrate the point to use 3 resistors. So we have R1, R2, and R3. Now, conservation of charge tells me that if you have 1 coulomb going in, 1 coulomb has to come out. So whatever current flows through R1 has to be equal to the current that flows through R2, and it has to be equal to the current that flows through R3. Okay. And then it has to come back, circle back. And so it would be the same current. In this case, the current will flow clockwise, right? So let's use our loop rule. Oh, by the way, the goal here is to ask the question, if I were to replace all these 3 resistors by just 1 resistor, what would it be?
R1 plus R2 plus R2.
Yeah, and that would be the answer, yeah. And then, that is the correct answer, yeah. So, what should I replace these 3 resistors with in order to keep everything else the same? I want to keep the current the same, so the same current will flow in the circuit, but I don't have 3 resistors, I just have one resistor. What should it be? Well, we will use the loop rule. The loop rule says, if you go around the circuit once, in a closed cycle or circle, you will get 0 change. So you go from here to here, you increase by the EMF, and from here to here you drop by V1, and you drop by an additional V2, and you drop by a V3. So you will get E minus the voltage across resistor 1 minus V2 minus V3 equal to 0. That's the total change. And this tells me that the EMF of the battery will equal to V1 plus V2 plus V3. But V1, according to Ohm's law, is I R1, and then V2 is I R2, and V3 is I R3. Again, in general, you will put I1 R1, I2 R2 plus I3 R3, but in this case, I1 is equal to I2 and it's equal to I3. It's the same current, since they are in series. Now, if I were to put their equivalent, it would have the voltage drop across the equivalent would equal to the same as the voltage of the battery. Remember when we only had 1 resistor, it was just the EMF of the battery. So it's equal to I R equivalent. So the current cancels, this I can be divided out. So you get R equivalent equal to R1 plus R2 plus R3. And if you have more resistors, you will have plus, 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 right? Yeah. So this is in series. When you have resistors in series. It should remind you of capacitors in parallel. When we had capacitors in parallel, their capacitance was C1 plus C2 plus C3 and so on. So that is that. Next one would be resistors in parallel. And then we'll do a couple examples. So let me do resistors in parallel before I do an example here. Probably won't do an example today, but so let's do parallel. So for parallel, well, they are connected in a way that looks parallel. So parallel they look like this. You got a battery, and you have a resistor. Let's call it R1, and then you have another resistor, R2, and you have a third resistor, R3, and this is the battery. Okay. Yeah. Oh, that was one. So you will have current flowing. This is only one battery, so the current will flow this way. So the current in the battery will flow like this. Flow. This is I. Now the thing is this, the current gets here. It has two paths. Some of it will flow this way and some of it will flow this way. The current that flows this way, we're going to call it I1. And then there will be some left over that will flow this way. And this current that flows this way will get here. And what happens? It splits again. Some of it will flow this way, and we're going to call that I2. And the rest will flow this way, and we're going to call that I3. And the question is, what is the relationship between I1, I2, I3, and this total current I? The junction rule says the current that goes into a junction, by the way, this point here where more than two wires meet is called a junction. So the current that enters into a junction, you see this one is going into this point and this one is going into that point?
Yeah.
Will equal to the current that comes out of that point. Has to equal to the current that comes out. So the current that goes in has to equal to the current that comes out. And that's the junction rule. So if you have, let's look at this junction here. What is the current that's going into it? I3 and I2. So the current that comes out has to equal to the sum. So it's I2 plus I3. Okay? That's the junction. And now let's look at this next one. I2 and I3 are going in. I1 is also going in. So what must come out? I1 and plus these two, right? So I1 plus I2 plus I3. And that flows through the battery, and that's equal to I. So these currents, I1 plus I2 plus I3, has to equal to I. So I should equal to I1 plus I2 plus I3. Okay. Now the question is this, ultimately is, if I were to replace all these resistors by one resistor, what would the equivalent be? Okay, yeah. So if I were to change it to make it this, so into an R equivalent, what should R equivalent be? Okay. Well, I know that V is equal to IR, so I will equal to what? Right here. V equals to IR. So I is equal to V over R, right? So for this one, the current, if I were to replace it by just one resistor, the current that flows through it is the voltage across it divided by R. Yeah, by resistance. And the voltage across it would be the EMF of the battery. So EMF over R equivalent. So on the left side, I got EMF of the battery over R equivalent. I1. I1 would be the voltage across R1 divided by R1, right? Plus I2 would be the voltage across R2 divided by R2. And this one would be the voltage across R3 divided by R3. Now the claim is V1 and V2 and V3, they're all equal, and they're just equal to the voltage of the battery. Why is that?
Conservation of energy.
You can say conservation of energy, okay? And how can we kind of convince ourselves?
Kirchhoff's loop rule.
You can use the loop rule. Okay, you can use the loop rule. Here is, I'm going to demonstrate it for R2 only. Right, so here is the loop rule. If I start at this, and here's my loop, by the way, I will use a different, let me use red. So here's the loop I'm going to take. I'm going to start here and go through this loop. Okay? But any closed loop, doesn't matter, the shape or, yeah. So if I go from here to here, what's the change?
E.
Yeah, the EMF of the battery, yeah. And then these are wires, so nothing.
Minus R.
And then I go from here to here, that's the voltage across R2, right?
Yeah.
And then nothing, and I'm back here, so that's equal to 0. So the EMF of the battery minus the voltage through across R2 equals to 0. That means the EMF of the battery must equal to the voltage across R2. So V2 has to equal to the EMF of the battery. And you can repeat that for this bigger circle or this smaller circle to prove that V1 and V2 and V3, they're all equal to the EMF of the battery. Or just think of the wires coming out of the battery. They're touching both ends of this resistor and both ends of this resistor and both ends of this resistor. So they're, all of them are experiencing the full battery. So, in other words, so V1, V2, and V3, they're just equal to the EMF of the battery. So since they're all equal, you can divide them out and you have 1 over. So that means, 1 over R equivalent will equal to 1 over R1 plus 1 over R2 plus 1 over R3. And that's resistors in parallel. Resistors in parallel, and they behave like capacitors in
Series.
series. Yeah. So, let's see. I have 4 minutes. Let me just mention one thing, and then next time we'll do the examples. How much energy is dissipated into a capacitor? How much energy will go through a capacitor? I'm sorry, I said capacitor. I meant resistor.
Oh.
What am I talking? We're in resistors right now. So let's say I have just a battery here. Here it is. And here is my resistor. And this is the battery. This is the resistor. And the current is flowing, right? Remember what the voltage is? It's a joule per coulomb. The amount of energy it takes to take a charge from one end to the other will equal to this. Remember the potential energy, the change in potential energy, that we call it du, is equal to dq times the voltage. You have this in the test. You have to apply this. Not in terms of dq, but it was just q times d. So du. Now, so since the voltage here is coming from the battery, this V is really V of the battery, the EMF of the battery. So I'm going to say du will equal to dq, and then the EMF of the battery. If I divide both sides by dt, or delta t, and take the limit, you would have du dt. Well, dq dt is also known as the current, right? dq dt is the current. So this is I, the battery, the voltage. du dt is the power, is the amount of energy per second. So this is how much energy the battery is giving you per second. That's the power. Power. Okay. So where is that power going? Well, the current will flow through here, it will go through the resistor. So let's see the du through the resistor, what would it be? For the resistor, du for the resistor would be dq, it's the same charge. So the battery took a dq from here and then it went through the resistor, times the voltage drop, right? It went from here to here, so its potential changed by a negative amount. And that negative amount is equal to the potential across the battery, right? So V of the, the potential across the resistor, but it's negative. Okay? So it's lost potential energy. The lost potential energy goes where? Heat, yeah, it actually goes into heating the resistor, some heat. So typically the resistor will be your, let's say, your cell phone being charged, or maybe your hair dryer, or maybe it's a heater, a heater. So it takes power from the wall, voltage from the wall, and then converts it into heat energy. So the thermal energy will equal to the negative of this, right? So the thermal, dE thermal will be dQ V, and, oh, sorry, let me just divide by dt, and it's equal to IV. I will continue this next time, right?
Yeah, but